So I think we start with talking about a violin, and then it goes to these rocks in New Zealand. Are y'all ready? Page 478. Cuba's ready. Does anybody in here play a string instrument? What's it called if it's string? Is it an orchestra? Yeah. So I was thinking about all the string instruments. We got the violin. That's what this problem's about. And then you got your guitar, your bass, your harp. Are there any other string instruments? Cello. The cello. So does anybody know out of all of those string instruments, which one has like the strings are like the tightest? They're like the most difficult to pluck. So we looked it up and it turns out it's the violin. It has the highest note, I believe is what I read, and I'm not a musician. So if you are a musician in the room, it's something to think about. I believe the highest note comes from the tightest string. What's the highest note called? Does anybody know? E. So it's interesting to think about how tight that string is, what wavelength it operates on, what its frequency is, and how it produces that noise, and then it goes into our ears and we perceive it a certain way. So the least possible frequency of a string is called its fundamental frequency. It's measured in hertz. I've heard of hertz before. Millibars yesterday. I hadn't really heard, but I've heard of hertz before, of a certain string on a violin. And this is the function. It's another square root function. That's pretty applicable here. T is the tension in newtons of the string. Okay, so for this, does it say violin in the problem? Oh yeah, violin. So this violin has a frequency of 196. So that's the N value. N is 196. So we'll plug it in. And that leaves us 196 is the square root of the tension divided by 0.0054. I'm interested in this number. What's that mean? Google it. You can Google this formula, fundamental frequency formula. You're allowed to look that up. When we talk about students having access to the internet to further their education, it wasn't for social media and math games, which is 99% of it. It was moments like this, like, wait a minute, like, what does this square root function mean? Take some time and explore it and look at different frequency along different string instruments. You know, we're allowed to look into that. Let's solve this. Yesterday we talked about canceling out radicals with exponents. So I'm going to raise both of these to the power of 2. So I should see lots of calculators or Google calculators or something. This is it. It's number 33. This is number 1 on Bellwart. I don't have this perfect square memorized. I don't know 196 squared, but here it is. 38,416 equals T divided by 0.0054. And the last thing to do would be to multiply by that denominator. That cancels it. And then we get to T equals 207.45. So I'm going to answer in a complete sentence. T is tension. And tension is measured in newtons. So, hey, tension's a little bit like pressure, right? Like air pressure. So we talked about air pressure yesterday. Now we're talking about tension. All right, go ahead and read the next one. This is about natural spheres in New Zealand. They're boulders, but they're not like rigid and cracked and disformed like we think of boulders. They're like, I'm just going to pull up the picture. They're like really smooth and rounded. So, kind of weird. What would make something like that in our natural world? Real smooth like that, you think? Maybe erosion? There's like a legend that it's actually petrified wood, that it was like carved out of canoes or something, and it's petrified wood. Someone said maybe it's dinosaur eggs. They're starting to fall apart, apparently. Those are cool. I would watch that YouTube video in my own time. Where are those things falling apart? I'm curious. The Meraki boulders are stone sphere along the coast of New Zealand. The formula for radius of a sphere has a square root in it. Does anybody know the formula for the area of a circle? We're close. It's something like that. Pi r squared, pi radius squared. All of your functions that you know that have something squared, they have another equation square rooted that's related to it. So pi r squared is the area of a circle. This is the formula for surface area of a sphere. And so area is squared, the surface area is square rooted. Those are balancing each other. So it says radius is 1/2 times the square root of surface area divided by pi. Find the surface area of a boulder with radius 3 feet. So that means r is 3. So we just got to plug 3 in. Hey, if the radius is 3 feet, what's the diameter? 6 feet. That's a big one. We're talking about the surface area of a pretty big boulder, 6 feet across. And it's all smooth and round. Weird. Can you guys solve it from here? Just had to plug in 3 for r. I guess I would cancel. You have to isolate the square root. That's what we talked about yesterday. So I'm going to cancel this 1/2 by multiplying by its reciprocal. Reciprocals are really effective that way. 6. I see a 6 also. So this is now 6 equals the square root of s divided by pi. How do we get rid of a square root? We square both sides. Square both sides. That's 36 equals s over pi. We're solving for s, so we'll multiply both sides by the pi. And so we're at 36 pi equals s. And so leaving the pi there is exact form. Go ahead and put the pi in your calculator and see what the approximation is with a decimal. And then answer in a complete sentence. Man, when I put 36 pi in my calculator, it just says 36 pi. Anybody else? Yeah, so just hit the button above enter and it'll go decimal for you. The surface area is approximately 113 feet squared. That takes a lot of paint if you wanted to paint a boulder. Yeah. How much does a gallon of paint do? How many square feet? Any painters in the room? Professional painters? No. That's it for bow work. Some word problems.
It's about 300 to 400 square feet.
In a gallon? So you could cover that boulder with like half a... Oh, but you probably do 2 coats, right? So maybe 1 gallon to really make it look nice. Sneak into New Zealand and paint their boulders. Just wake up one day and all those boulders are different colors. It'd be fun. I wonder if they're like protected. What's with these weird boulders? Maury Legend says the boulders are gourds from a canoe wreck that turned into stone. Have you guys ever seen petrified wood? Looks like stone. It's weird. Oh, you have? Minecraft is so educational. If you go out to like, I think it's Nevada, there's the petrified desert. Anybody heard of that? Near the Grand Canyon? Yep. And it's wood. I don't know. I shouldn't talk if I don't know for sure. So let's just. All right, let's look at yesterday's assignment. Yeah, it looks like stone inside. Petrified wood. Like, what's the typical? Like, what makes it rare? Is that dessert or desert? Yeah, it kind of looks like rock, but it's just wood. Petrified forest. So does anybody want to ask questions about yesterday's assignment, which was odd? It was 1 to 21 odd. Anybody have questions about that? We got 19. There's 19. If you had a question about 19. Wonder what kind of rock those stones are. I mean, first things first. Y'all want to just start today's assignment?
Yeah.
Alrighty. It's so similar. I couldn't say it's the exact same, but it's so similar. There's a beautiful example right here on page 476. When an equation contains a power with a rational exponent, you can solve the equation using a procedure similar to the one for solving radical equations. Isolate the power, raise each side of the equation to the reciprocal of the rational exponent. The reciprocal here is super effective. So look, it's not a radical anymore, but all chapter long we've been saying how these fraction exponents are just like radicals. So the first thing you would do is subtract 2, isolate it. And then what do we do with the 3/4? If you raise it to 4/3, it cancels out. I'm going to show it a little more clearly than the book does. So it's 2x to the 3/4 equals 8. Now watch if I do 4/3 right next to 3/4. I have to do it on both sides, of course. But 3/4 times 4/3 is just 1. So that gets rid of that exponent over there. I'm going to show that here. You don't have to show this, but 3/4 times 4/3 is the same thing as 12/12, which is 1, which is what makes it all disappear. So the reciprocal here is super effective. Just gets rid of the exponent where you don't want it. Cancels it out. So now I have 2x equals 8 to the 4/3. So 8 to the 4/3 is 16. Divide by 2, you get x equals 8. I've highlighted this. It's super important. Always check for extraneous solutions. So yesterday, it was towards the end of the assignment, you were seeing solutions that were coming out, but when you plug in, they don't work. You must plug these answers in to make sure they work. So extraneous solutions still exist here, even though you don't see a radical. Eight to the 4/3 is? I'll remind you, 8 to the 4/3 is the cube root of 8 to the 4th. So that's 2 to the 4th. So that's 16. All right, so your book doesn't outline steps like it did yesterday. So here's some steps for you. It just shows the one example, and then it just assumes you got your steps from there. Very similar steps to yesterday that we read through the book. Number one, isolate the base and the exponent. So that's why in that first step they subtracted 2. Number 2, raise both sides to the reciprocal of the exponent. I don't believe you've ever done that in a math problem ever. You've never done the reciprocal of an exponent. So that's brand new practice for you. Use properties of exponents to simplify. Solve and check. Right here, this may require quadratic skills. So students aren't getting stuck at the exponent part. They're getting stuck at factoring. You're going to have to factor here in some of these. Always check. This is your assignment today. I'm going to let you have time to write this down and jump into this, and then I'll start doing some problems with you. The square root of 8 is 2 square root 2.